What is happening, physical science folks? This is Mr. Call. Today we're going over some slides and information on radioactivity and stability. These are some big ideas. We got a test coming up, and so I want to make sure you feel really comfortable with these ideas. Let's start with something that we are familiar with. I know radioactivity and stability are not two topics that we've really gotten into yet, so let's jump into something that we do remember. Bohr's model of the atom. Remember, atoms don't really look this way, but we represent them this way because we can see where the protons are, where the neutrons are, and where the electrons are. This is carbon. So we have a regular atom of carbon that has 6 protons, 6 electrons, and 6 neutrons. It's stable. This is exactly how it looks on the periodic table. Okay? This shouldn't be a huge new idea to you. But let's go ahead and move things around a bit. Let's change things up. What if we removed a proton? What if we mess with the number of protons? Here's what happens. If we just take one proton away, so it only has 5, and we leave the other electrons where they're at, it's not even carbon anymore. It's boron, okay? So a big idea here is that the number of protons really determines which type of atom you have on the periodic table. Protons represent that. So if you change protons, you change the element that you have. Let's restore carbon back to all of its protons, neutrons, and electrons. But then what if we add a neutron? Let's go ahead and change that about it now. There's an extra neutron here in the nucleus. Notice that now it's still carbon. You can change the neutrons and not have it actually be a different element, but all it is now is carbon, but it's heavier. It's heavier than it was before, and this is what we consider or call an isotope. All right? So an isotope is any atom that has more or less neutrons than it normally does. But carbon is still carbon as long as it has 6 protons. Okay? Now let's change those electrons. If we leave protons and neutrons alone and we change the number of electrons, watch what happens now. So 6 protons and we have 6 neutrons, but we've added an extra electron out here in this outer energy level. It's still carbon, it's still stable, but what we have now is an ion. An ion is an atom with charge. It's either got more negative things or more positive things. And so there's actually 2 kinds of ions. If the atom has more positive things, more positive protons, then it's considered to be a cation. Okay? And if it's an atom that has more negative things, more negative electrons, then we call it an anion. The way I remember this is that in the middle of cation there's a T that kind of makes a plus, and that helps me remember cation is an atom that has, or an ion that has more positive charge than negative charge. Okay? But hold on, there's more. Isotopes. Remember, isotopes is a word we just barely introduced, and it's an atom that has more or less neutrons than it normally does. But the trick is, not all atoms that are isotopes are stable. And what does stability even mean? Well, know that the atoms on the periodic table, for the most part, are stable, meaning they don't want to change. Okay, they don't want to become anything other than they are. They're relatively happy with their identity. Okay, but if we have carbon here with 6 protons, but we remove one of the neutrons now, so we only have 5, this is now labeled as unstable. If you are on the PhET lab where we built these atom simulations, the nucleus would shake. And all that means is that carbon with only 6 neutrons being unstable means that it doesn't want to stay that way. It's going to try and change. It will follow certain rules to change, but it's going to try and become something different so that it can become stable. And this is where radioactive decay comes in, radioactivity. There are 3 types that we want you to know. And this is out there, okay? So stay with me. One of the things that an atom can do if it is unstable is it can decay by something called alpha decay. Alpha decay is when that atom in its nucleus will actually shoot out 2 protons and 2 neutrons, which is exactly what a helium nucleus looks like. It'll get rid of it. It'll shoot that out of the nucleus, and we call that decay. And it will leave that original atom stable. Okay? Another option that an atom has to become stable, if it's unstable, is beta decay. And this is when one of the neutrons in the nucleus, okay, remember a neutron has no charge, it will actually turn into a proton and an electron, and it will shoot off the electron, leaving another proton in the nucleus, which changes the identity of that atom, right? Remember, protons determine whether it's carbon or whether it's oxygen or whether it's nitrogen. So this is another form of decay, different than alpha, and so we call this one beta decay. And the last one is by far the most intriguing to me. Gamma decay is where in the nucleus of the atom, a gamma photon or energy leaves the atom to make it more stable than it was before. Okay? Those are three types of decay. Now, we're not going to expect you to be able to know, okay, when carbon-14 decays, which type of decay does it use, alpha, beta, or gamma? But what we do want you to know is that there are three types of decay, and we want you to know what happens in each one, okay? So be familiar with alpha decay is when 2 protons and 2 neutrons leave the nucleus. Know that beta decay is when a neutron splits into a proton and an electron and sends the electron away, leaving a proton behind. And know that gamma decay is basically this gamma energy leaving the nucleus. All right, so know the three types and know that they happen, but you don't have to know which type of decay each unstable atom undergoes to become stable. All right, so a couple of questions. Why do atoms even decay? Not all of them do, but why would an atom decay? And the answer is very straightforward: stability. Atoms on the periodic table are after stability. They want to be stable, okay? And one of the things they can do to become stable is decay if they are already unstable. All right, so how long does it take? If an atom is unstable, how long before it can be stable? And this is a really cool, intriguing idea, so stay with me. It's called a half-life. If an atom or a collection of atoms are unstable and they're going to decay, it takes one half-life for half of that material to decay and become more stable. This is an interesting idea. A half-life is the time it takes for half of that radioactive material to decay, or that unstable atom to decay. And so here are some examples, right? Let's just say we have 100 atoms, and they are unstable, and they are going to decay to become more stable, all right? So 100 atoms, right? After one half-life, we'll tell you how long that is in just a second. After one half-life, 50 of those atoms have decayed and become something different and more stable. And 50 of those atoms are still unstable. Okay, they haven't decayed yet. If you let another half-life pass away, half of this half will decay and leave 25% of the original, so 25 atoms to decay, are still unstable, right? So a half-life is not half of the original amount and then it just takes one more half-life and we're done. These unstable atoms keep dividing in half and in half and in half, and only 50% of them become stable at a time. And that's a unique thing of half-life, right? So walk through this one more time. 100 unstable atoms. After one half-life, 50 are stable and 50 are still unstable. After one more half-life, this blue section divides in half, and this half becomes stable, and we're left with these 25 atoms that are unstable. After a third half-life, you cut this in half again. See why we call it a half-life? And approximately 12% is unstable, and approximately 12% became stable, right? After a fourth half-life, it cuts in half. Are you seeing the pattern? So a half-life is the amount of time it takes for a group of atoms. Half of them decay and half of them do not. All right? So here are some common half-lives. This is the other cool part about this. A half-life, that amount of time, is different for each type of unstable atom. For example, oxygen-19 is not your normal oxygen. It's unstable. The time it takes for one half-life to pass away for oxygen-19 is about 26 seconds, right? If you wait 26 seconds, half of those atoms will have radioactively decayed, and the other half are not. Okay? Cobalt-56 is not your normal cobalt-56. Look at the half-life here, about 77 days. That's a little different than 26 seconds, right? 77 days have to pass away before half of that cobalt-56 decays and becomes more stable. Mercury 194, approximately 444 years. Look how different these are. And plutonium 244 is an example that's just ridiculous. 80 million years before half of that sample will radioactively decay. All right. This is a concept that we're going to have to work with and become familiar with this terminology of decay and stability and radioactivity and half-life. And so our lab today that we're going to do, or at some point in the future, will have to do with dice that we will roll to represent this idea of half-life and decay. All right? These are new concepts. These are tricky. Please get my attention. Speak up if there are questions about these ideas. Shoot me an email. Get in the chat. In our next WebEx class or whenever we talk again, make sure you let me know where you're stuck. Okay? Have a great day.